There are 4 wave behaviors that are specific to 2D waves that we're going to talk about. The first is reflections. So here you see a wave traveling toward the end of the pan. It's pretty much a straight wave, a wave front. When it reaches the end, it bounces off and returns the way it came, exactly the same shape. No difference. In the second one, we're just going to see a reflection at an angle. So it goes toward the edge of the pan at an angle, and now look at what's happening with the reflection. It's also reflecting at an angle. When you watch that angled reflection reach the bottom of the pan right here, notice how it reflects off the bottom of the pan at an angle as well. And it will keep doing that until it runs out of energy. The second wave behavior is called diffraction. So I'm going to send a straight wave toward that opening between the 2 blocks, and notice what happens here. Most of the energy I sent toward the blue blocks has rebounded back the way it came. That's a reflection. But there's also this bit that goes through the blocks. The straight wave has become a circular wave as it passes through that opening. Here's why that happens. Water molecules are all attached to each other. So let's think about this line of water molecules here. Here comes the energy, and as it passes through the gap, it's passed on to the center molecules right in front of that gap. But because the molecules on either side of those central molecules are also attached to it, they are pulled along for the ride. They just are a little bit behind the center molecules. And that effect just becomes more and more pronounced as time passes. The center molecules are traveling the fastest, and all of the rest of them get pulled along more slowly behind. And if we widen the gap between the 2 blocks, the only difference is that the circle gets a little bit bigger. The diffraction is not quite as pronounced. We can also say that the radius of curvature is larger. Here's a simulated version of diffraction. So this water wave generator is going to create some straight waves, and then I'm going to throw a barrier in there with 1 slit. Now this doesn't show the reflections on the other side of the barriers, it just shows the diffraction part, the part of the energy that's traveling through the slit. Now if I put in 2 slits instead of 1, I get 2 sets of diffraction. And I end up with kind of a strange pattern going on. And this brings us to our third wave behavior. It's called interference. So the pattern that these 2 sets of waves create together is due to the fact that they're interfering with one another. We did that with one-dimensional waves. We called it superposition or interference. So that's exactly what's happening here. It's just that the pattern is a little bit more complex than the one-dimensional one. Let's look at this another way. We're going to have 2 faucets dripping into this pond, I don't know what this is, into this pool of water. Okay, now I want you to notice the pattern that's created here. It may take a moment for you to see what you're supposed to see. So let's first of all check out some lines. You see this fuzzy line here? And this fuzzy line here? Those are called nodal lines. So these bright patches here, these are crests, water crests. So we're looking at this from above. These dark patches, these are troughs. And so look down the center over here. You see bright crests and dark troughs. But in the middle here, you just kind of see fuzziness. There are no large crests or deep troughs. They've canceled each other out. And so we'd call that a node, if you remember that from standing waves. So nodes are where only destructive superposition is happening. And so along this line, you get only destructive interference or destructive superposition, which means that this is just a flat section of water. Whereas over here, down the center, you get an antinodal line or an antinodal area where you get large crests and large troughs. And that's happening on either side here as well. Now, if we increase the frequency of the dripping, let's just bring it up to the max, which doesn't end up being very fast, but look what happens to the number of nodal lines and antinodal lines. We now see a nodal line 1, 2, 3, 4 places, and antinodal lines we see 1, 2, 3, 4, 5 places. The number of lines has increased with the frequency. Now, this happens in water, but this also happens with sound, notice all of the antinodal lines, and the nodal lines. Okay, so what this means with sound is that these antinodal areas have large amplitude. And if you remember, amplitude is where the crests are tall and the troughs are deep, right? That's amplitude. It's the height of the wave. And as far as sound goes, we hear volume when we're talking about amplitude. So in all of these areas, if you'd be standing right over here, you'd hear a loud volume from both speakers. But if you're standing on this line over here, you probably wouldn't hear quite as much. Now, it's not like if you stand here, it's going to be silent. That's not really how it works. But you may hear a difference in volume from standing right here to standing right here. And so that's why speaker placement, if you're going to be setting up a home theater or something like that, is actually pretty important. We can do the same thing with light. Now, you're probably not going to experience this very much in your own life, but it was very important for when the nature of light was being studied. So it was discovered by Thomas Young that light experiences interference as well. So let's turn both of these on. And what he noticed, by putting up a screen at the end of this experiment, that there were bright spots and there were dark spots on the screen. So this happens because on this antinodal line we have large amplitude, and in the case of light that means a high brightness. And on these nodal lines we get no amplitude, which is a spot of darkness. And so he noticed that there must be interference going on. These must be waves interfering with one another because of these bright spots and these dark spots. Thomas Young did this with two slits rather than two sources of light, but it works the same. The last 2D wave behavior that we're going to talk about is refraction. Now, the easiest way to look at refraction is what happens to light when it passes from one medium to another. And what we mean by medium is a material that something is traveling through. So here we've got air on the top and we've got water on the bottom. You already have experience with this. If you are standing in a lake, sometimes you can see your feet and they do not look like they are where they should be. Or you put a straw inside a glass of water and it looks like it bends. So when we press our laser button here, it's sending out light waves to the boundary between the air and the water. And notice what happens. Rather than continuing along the straight line it was going on, it bends, changes direction into the water. Now you also get partial reflection over here, which you have also experienced when you are at the beach at sunset. The light from the sun is bouncing off the surface of the water and blinding you, but it's also passing into the water somewhat as well. So you've got partial reflection and you've also got partial refraction. So refraction is the bending of light or another kind of wave, changing direction, changing speed as it passes from one medium to another. Now we're going to talk about that much more in depth a little bit later, so that's where we're going to leave refraction. So we've talked about reflection, which is the bouncing of waves. We've talked about diffraction, which is the curling of waves around a barrier. We've talked about interference, which is when waves interact with one another and cause a different pattern to emerge. And the fourth one was refraction, which is the bending of a wave or the changing direction when it reaches a new medium from an old one.